Hello, my name is Christian Bishop, and this is my Lab 6 presentation on magnetic molasses. I'll start by explaining the purpose of the lab, walk through the experimental setup, summarize the glow strip, and compare the real data to the simulation, and end up with key what-if questions to help us understand the physics more deeply. The main purpose of this lab was to collect and analyze data of a bar magnet falling through an aluminum tube, and then compare the experimental data with the computational glow strip model. This comparison helps us see Faraday's law in action and understand how changing magnetic flux induces currents that oppose motion. According to the fundamentals listed in my slides, Faraday's law, Biot-Savart law, Newton's second law, time derivative of magnetic flux, and magnetic force, all of these play a role in magnetic motions. Previous results were the experimental time was 1.21 and the computational time was 0.85 seconds. Model assumptions. In the model, the bar magnets act as a magnetic dipole and the aluminum foil constructs the tube. We made several simplifying assumptions. Air resistance is 0, only gravity and magnetic forces act on the magnet, and the magnet behaves as an ideal dipole. These assumptions help isolate the magnetic interactions without complicated effects. Procedure, experimental setup. We identified the north pole of the magnet. We dropped it 5 times on a vertical aluminum tube with the north pole facing upwards, and recorded the time each time, and then averaged it out. The system contained just the magnet in the tube, and the surroundings included the room and everything else. From our experimental data, on slide 5, our tube length was 0.3 meters, our inner radius was 0.026 meters, our outer radius was 0.032 meters, our magnet mass was 0.025 kilograms, and our dipole moment was 4.48 amperes per meter squared, and our average fall time was 1.21 seconds. Checkpoint question: why not use a ferrous or steel tube? Because steel is magnetic, it would distort the magnetic field and completely change the induced currents. Why does the magnet fall slower than in free space? As it falls, the changing magnetic flux induces currents in the aluminum, which is the opposite in magnetic force. Lenz's law, this slows the magnet compared down to free fall. The glow strip model. The model constructs the tube out of many ring segments. The magnet acts as a dipole. There's a loop that updates position using Newton's second law, and there's also a velocity versus time graph, which we'll see in a second. Simulation also colors each ring depending on the direction and magnitude of induced current. The red and the blue show opposite current directions. The model predicts a fall time of 0.815 seconds, noticeably shorter than the real value. Here's more of our code here. You can see that loop. More code here. And here's our velocity versus time graph. Simulation. Which color responds to clockwise versus counterclockwise? Using Lenz's law, the color showing in the current that opposes magnetic motion corresponds to the counterclockwise direction when viewed from above. In this case, red is counterclockwise and blue is clockwise. What happens if you flip the magnet? If all time stays the same, only the direction of the current reverses. Why the simulated time is shorter than real time? The model ignores air resistance and human reaction time when the timing drops. What does the velocity versus time graph tell us? Inside the tube, the magnetic force bounces gravity, giving a region of roughly constant velocity. Near the exit, gravity becomes stronger than the magnetic braking force, so velocity increases in magnitude. Sources of air. Stopwatch was not super precise, and there was human air present for sure. Air resistance also affected the falling magnet, so it made the time longer in real life than it was in the computational model. And finishing up with our what if and why questions. What if the resistance on the conductor was reduced to super close to 0? How would it change the dynamics of the falling magnet? The lower resistance would increase the induced current and create a stronger force against gravity. The magnet would take longer to fall. Yeah, so basically there'd be more magnetic force against the magnet. And then what if there are holes and slits in the sides of the tube? How does this affect the rings in your model? Less rings would be present in the tube, which would make it overall weaker, opposing magnetic field, causing the magnet to fall faster.